Okay, how's it going? All right. Oh, all right. This is a much better day then.
You having a good day?
I'm doing all right. Students were a little slow on the last exam, but it happens. Yeah, I did. Questions about anything before we get going? All right. A few people missing. All right, let's see here. So we've done some stuff with the hypothesis testing ideas. So let's see if we can start applying some of these ideas to some of the more familiar statistics and distributions that we've computed so far, well, this semester and last. So we started this off talking about population proportions. Let's look at 7.1-6 on page 350. So the problem is set up as there's one side of the die that's heavy and the other side of the die, another side of the die that's light. So they are keeping track of the number of times a 1 is rolled and see if it's out of whack with what the probability should be. So it's number 6 on page 350, 7.1-6. So the hypothesis goes that, well, the hypothesis being tested, I should say, is that if I got a heavier one side, then it's going to land more often on that side, so you're not going to see as many 1s as you should if it were a fair die. So the hypothesis test is that the null hypothesis is the probability should be a sixth, versus the alternative hypothesis that the probability is in fact less than a sixth. The experiment was that they rolled the die 8,000 times and saw heads 1,265 times and wanted to know, okay, is that enough evidence to say, well, yes, the one side is heavy and it's not a fair die? Well, certainly, if I divide 8,000 by 6, we get what? Well, 1,300 something. 1,333. I did that right. 8/6, the same thing as 4/3, so it's 1333-ish. So you would expect to see about 1333 heads if you rolled at 8,000 times, or heads. Thinking flipping a coin, sorry. 1,333 ones if you roll the die 8,000 times. So this is definitely fewer than what we would expect, but is it unreasonably fewer than what we would expect? Okay? So the idea, of course, then, is to try to compare it to something that we know. Well, this is a binomial experiment, which would take a while to try to figure out the actual critical region, if you will, using the binomial distribution. But we know that if your n's large enough, you can approximate the binomial with the normal, right? That's central limit theorem idea. So approximating the binomial with the normal distribution, if we think about what the picture would look like with a normal distribution, you would have your mean here, right? You're trying to see if something is below the mean, essentially. So we're looking at your critical region being out here on the left. And we want this critical region to have a probability that's low. And in this particular problem, they want our alpha to be 0.05. So we want the probability that our test statistic, whatever that happens to be, the test statistic is in this region. This is assuming the null hypothesis is true. The probability that that test statistic is in that region, in this case, is that 0.05. That's the alpha they told us in the problem. That's the alpha. Okay? So that region that I put in there on the distribution, that's our critical region. If we land in that region, we're going to reject. And what the problem in this case says that as long as that probability is 0.05, that we land in that region, we're going to go ahead and say, well, then the null hypothesis probably isn't true. Again, we pick that alpha level, we pick that significance level, saying, is it small enough to say, okay, it's probably not true? Now, depending on what the scenario is, your small enough might vary. It might be 0.1, it might be 0.05, it might be 0.01. It just depends on the context of what you want to say is good enough, close enough, small enough. Okay? So in this problem, they defined it for you. They said it was 0.05. Right? So we have to calculate the test statistic based on the type of distribution we have, or based on an approximation of the type of distribution we have. Most of these are going to go back to normal or t. Of course, when we start talking about variances, we'll start using chi-squared and f. Okay? But for means and population proportions, we know that we can approximate it with normal. If it's a large sample, we can approximate the sample means with a normal, and difference of sample means with a normal. If it's too small, then for means we'll use t. Right? But in all those cases, again, we're trying to basically identify this critical region with some sort of a bell-shaped curve. In this case, also, since we said that the proportion was definitely less than a sixth, we put all of the probability on one side. This is what's referred to as a one-tailed test, because we're looking at either we're less than what we purported the value to be, or greater than what we purported the value to be. That's a one-tailed test. If all we were doing was purporting that it's different, so for example, if we want the means to be different, or if we wanted the variances to be different, that would be a two-tailed test. It could be above or below, and you would split that significance level in half. Put half of it above, half of it below. And that would be your critical region in that case. Okay. But in this case, since we're doing the one-tailed test, we're putting it all on the left side. And then again, since we've got a large sample here, our n is 8,000. And certainly we said that we can use a normal distribution to approximate the binomial as long as our n times p and our n times 1 minus p are both bigger than 5. Well, 8,000 times a 6 is well above 5. Okay, so that normal distribution idea should work just fine. All right. So when we do our test statistic, remember for the binomial, we use that normal approximation, and thinking about it in terms of the mean idea, we did the p hat. That was our sample statistic, right? That's just the y over n. So in this case, that would be the 1265 over the 8,000, whatever that happens to whatever that turns out to be. We would expect, in this case, the 1/6, because the null hypothesis is p is equal to a sixth, right? Now again, this is for the population proportion. We're doing it with the central limit theorem. We also know that in this case, the variance is your p times 1 minus p over n. But again, we're assuming the null hypothesis is true when we're trying to calculate the probability of where our test statistic landed, right? So we're assuming that the null hypothesis is true. In that case, our p is 1/6. So our variance would be 1/6 times 1 minus 1/6 over the 8,000. My apologies. I don't want to use the 1/6. Sorry. My apologies. I want to actually use that p hat. I'm glad I checked that before I went on. We're going to... Oh, no, I lied. I was right the first time. I was confused by what I was reading that out of the book, and I'm looking at the book, and no, this is definitely 1/6, because we're assuming that the null hypothesis is true. I read the p naught and thought p hat. Sorry. We're assuming the null hypothesis is true. If the null hypothesis is true, we're assuming that where we're drawing the sample from should be a probability of happening of 1/6. So the variance would definitely want to use that p. Okay. If I were trying to do power, I would base it off what the alternative hypothesis is, which would be hard in this case because we wouldn't have a hard and fixed value for the p. Remember, for power, that's the trying to calculate the probability of not rejecting when we should. If I just say that the p is less than a 6, that's hard. Right? Because I don't exactly know what the p is. So the probability that I didn't reject when I should have would depend on what the actual p value is. Okay. So it's a harder question to answer, that's a question we're going to at least try to get a handle on later this semester.
Why is it over the 8,000?
That's the central limit theorem idea again. When we're dividing by when we have the things being run over and over and over and over again, we divide by the sample size.
Okay.
Or if you like it better this way, if we just did p hat minus p over square root, not p hat. If you did y minus np over p times 1 minus p. So this would be counting number of successes. This would be mean number of successes. This would be your, this should still be, the variance would be n times p times 1 minus p. And then divide top and bottom by n. And you get that over n piece here for your variance. All right. So our sample statistic then, in this case, is you're going to take your p hat, which is your, what was that, 1265. Your test statistic will be that 1265 over 8,000 minus a sixth, and then it's divided by square root of a sixth times 1 minus a sixth over 8,000. Get this part here. Now what do you get for that? Yeah, I have a business calculator in there. I'm not doing it on that.
It's supposed to be negative.
Yes, it should be negative because it was below. Yeah.
Negative 2.05.
0.05?
Right.
Sounds like a good number. Okay. I like the way the number sounds. Okay, so we need to know, is that test statistic indicative of rejection or not? Is it over here in this critical region? Well, we said we want this value to be 0.05 for this probability here, and we're using a normal approximation. So we standardized everything, right? We subtracted off the mean and divided by the standard deviation, so we standardized it. So we made this into a standard normal, or at least an approximating standard normal. So we should be able to figure out what this value has to be if one the probability being less than that is 0.05. What value is that?
Negative 1.6.
Yeah, that should be the negative 1.645 one. Yeah, good. I'm glad you remembered that one. Yeah.
That's the only one I remember.
That's the only one you remember? That should be negative 1.645. Hey. Maybe. Erase. So,
That point.
what's that?
That point.
The point we're right here. Yeah,
Okay.
yeah. So we refer to that, so we call that region the critical region, so that value for Z is the critical value in this case. So our critical value is negative 1.645. And so we can define the rejection in terms of critical value versus critical region. Remember we said we would reject if we're in the critical region. Well, the critical region is defined by this critical value, so we would say we would reject H naught if the test statistic that we just did, I'll call it Z because we're doing normal approximation, if our Z is less than negative 1.645, which it is in this case, right? So in this case, we would reject H naught. And in other classes, I would be a little bit more worried about making an actual honest to goodness conclusion statement that is relates back to the context of the problem. So in this particular case, you would say that there is sufficient evidence to conclude that the true proportion of ones that occurs is less than a sixth, something along those lines.
You did it as you just did.
Yeah, I'm sure she did. Yep, I'm sure she did make you say that over and over and over and over again. Yeah. In this case, I'm just worried about whether or not we would reject. Now, is there a different significance level based on that test statistic where we wouldn't reject? Say you wanted alpha equals 0.01. If alpha is 0.01, then your critical value in that case would be negative 2.33. Would you have rejected in that case? No. So this test you would reject at the 0.05 significance level, but would not reject at the 0.01 significance level. There's not enough evidence to reject 99% with what would be essentially 99% certainty. Does that make sense? Another value that's associated with hypothesis testing is what's referred to as the p-value. So we have this observed value of our p hat. The p-value would be, let me draw the picture first and then write out the words or the symbols, depending. All right. We had I'm drawing in terms of normal distribution because that's what we're using to approximate this thing, right? We had our mean, we've got our critical value, whatever that happens to be. I didn't write that negative 1.645 very nicely because that mean, I wrote mu, and then I wrote negative 1.645. That would assume the mean was 0 because I converted it to a z-score. So I mix-matched with the way I drew my distributions, but you're always going to convert everything to standard normal to look it up in the table anyway. So, all right, so your critical value is out here. So this is your significance level, the alpha, right? Now we also calculated our test statistic, so whatever's out here. In this particular case, the test statistic landed in the critical region, right? Okay? When we're talking about p-value, p-value says, okay, still assume that the null hypothesis is true. If you took any other sample, what would be the probability that you had that sample or better, better from a rejection standpoint? What would be the probability that you had that sample or better as evidence that you rejected? So your p-value talks about this probability in here, down even further. Okay, so your p-value is this probability. So it's the probability, in this case, it's the probability that another sample lies below our test statistic. That's what the p-value is. So the probability that you're at that value or lower is what the p-value is. So it could be higher than the critical value or the significance value, without a doubt. The significance value is set from the outset. It has nothing to do with anything except that I want to make sure the probability of making a type 1 error is that value. That's the significance of the hypothesis test. The p-value is based off the test statistic that you got. Okay? And from the test statistic that you got, you base it on being there or lower, in this case, because we were doing a one tail below the mean, right? If we were doing one tail or above the mean, you would have gone there or higher. And if you do two tails, you would do 2 times wherever it landed. If it was below the mean, you would do the probability that was below it and then multiply by 2 because you got to go to the other side of the tail. And then vice versa, or above the mean. We'll talk more about p-values as we go along. That's the definition for your p-value. Okay? So in this case, to figure out what the p-value is, you would look up your 2.05 in your table, because that was our test statistic, right? We would look up the 2.05. Say the right words. Saying the correct words is difficult for me today. 2.05, look it up in the table, you get 0.9798, subtract it from 1, so we would have 0.0202, looks like. So in this case, the p-value is 1 minus, it's phi of negative 2.05. So that's 1 minus phi of 2.05. Which I just said was 0.0202. In this problem. Everyone okay? All right. Let's do number 10, same section, and then we'll do one with means. Number 10 says you got P is a proportion of drivers who did not proportion of drivers who use a seatbelt in a state that does not have a mandatory seatbelt law. I'm not even sure those exist anymore. It's claimed that that proportion is about 14%. So the Department of Motor Vehicles decided, hey, maybe we should get the word out that seatbelts are important. Put out together an advertising campaign. 2 months later, they said 104 out of 590 were actually wearing their seatbelts in a random sample. So the first part it asks us to do in this number 10 is define your null and your alternative hypotheses. All right. So what's the null hypothesis in this case? Yeah, that's the p is equal to the 0.14, right? Because it said that it was claimed that p is equal to 0.14. And we're trying to see if the advertising campaign had an effect on that. So what's our good Lord, why can't I not talk today? What's the alternative hypothesis for this case? P is greater than, good. Because we want to know if it actually had an effect. It got more people to wear their seatbelts. Okay. The next part, it says that we want to define a critical region with an alpha equal to 0.01 significance level. Given the type of test we wrote down, is this a one-tail or two-tail? One, because we're going above the purported values. It's a one-tailed test. So we don't have to worry about splitting anything in half. So again, from a picture standpoint, our critical region is going to be up here. We want this probability to be 0.01. So we need the critical value from our Z table. It should be 2.33. It'd be 2.578 if it were a two-tailed test. It should be 2.33. I don't know if it goes to 3 decimal places out here or not. 2.326. Nope, sorry. Yeah, 2.326, yeah. So 2.33. I'm going to leave it at 2.33. If you do 3 decimal places, it's 2.326. All right. So there's our critical region. So we're going to reject if our test statistic in this case, so I'll call it Z since we're doing a Z score, we're going to reject if Z is greater than 2.33. So to calculate our test statistic, remember again, we're going to do our point estimate minus what our null hypothesis says it should be. In this case, it said that there were 104 out of 590. So we're going to do 104 over 590. Subtract off the purported value, which in this case is 0.14. And then divide by 0.14 times 1 minus 0.14 over 590.
$2.54.
2.54. The reason why they're making these numbers like this is to make sure that you are getting the right critical values for one-tailed versus two-tailed tests. If this were a two-tailed test, your value would be 2.578, I believe, for your critical value, and you wouldn't reject at 0.01 if it were a two-tailed test. But this was a one-tailed test. Would we reject in this case? Is it bigger? Yeah. So in this case, we would reject. And again, I'm not going to worry about concluding statements. Just tell me whether or not you reject it. I know Dr. Lee would be very disappointed in me. I mean, well, it's the same sentences every single time. It's just writing in terms of the context of the problem.
Would give us a sentence and then just like leave the blanks of the stuff we would change. So like for the problem, we would just put in the blanks.
Oh yeah,
basically. That's
what they do. When they do this stuff in online homework packages, that's exactly what they do. They have little drop-down menus where you would or would not reject, and then there is sufficient evidence or there's not sufficient evidence, and you're just filling in the blanks. So now for my 130 class, when I do this later this semester, I will make them write out the words. But
Is that the same thing you did?
it's the class that would be kind of before that one. Yeah, but it's the same. Yeah, yeah. All right. That okay with everybody? All right, let's see if we can do one with some means and then do one with difference of means, and then we'll talk about variances as well. So let's look at the next section, 7.2, and let's look at, well, let's look at number 7.2-4. We're going to be looking at the thickness of spearmint gum from vending machines. Sounds like fun, right? So the target thickness is 7.5 hundredths of an inch. Almost screwed that word up too. We're going to test it against a two-sided alternative hypothesis. So they just want to know, is the target thickness of 7.5 really happening? So not is it bigger, is it smaller, just is it different? Okay? So our null hypothesis then is that the mean thickness is 7.5 hundredths, or 0.075, but since they wrote it that way. 100. There's a D in there, isn't there? Hundredths. Whatever. I'm about ready to write it as 0.075, so I don't have to worry about spelling it. Yeah, there's a D in there. Good. All right, so then the null hypothesis in this case is that mu is just different from, right? Not equal to. Yeah. Now, in this problem, they did not tell you what the variance is. The variance is unknown. And the sample size they gave us is only 10. So normal is not going to cut it for this one, right? Instead, we'll have to use t. So when we do our critical values in this case, we'll need to make sure that we go grab a t value, not a z value. So if this were two-tailed at 0.05, for a z, you would go grab 1.96 because you got to split it into two pieces. So you would have 1.96 and negative 1.96 for your values. Because you would need to split it as 0.025 on both sides. Does that make sense what I'm saying? We did 1.645 earlier for the one-tailed test at 0.05 significance. But in this two-tailed test, you have to split it in two. So if it were normal, you would go grab 1.96 because it would be 1.96 and negative 1.96. But we can't use normal in this case because it's a small sample, so we have to use t. How many degrees of freedom will we have in this case for t? 9, right? Because it's one less than the sample size. So you would go to your t table. I would want t sub 0.025 because it's two-tailed. And look at 9 degrees of freedom and get 2.262. All right, so again, the 9 is coming from the fact that we've got n equals 10. And the 0.025 is because we got a two-tailed test. Does that make sense? Okay. So then, again, from a picture standpoint, T looks like normal. It's bell-shaped. It's just not, oh, it's kind of bell-shaped. We'll pretend like it's bell-shaped. It's bell-shaped. It's just a little bit steeper. So we've got a negative 2.262, and we've got a positive 2.262. So our rejection region is there. So if it's above the 2.262 or below the negative 2.262, we'll reject it. Is that okay? Okay. All right, so we calculate our test statistic. So we need to figure out what our mean and our standard deviation is. Let's just do that in Excel real quick, because I want to show you something else in Excel here in a second. So the values, we got 7.65, 7.6, 7.65, 7.7, 7.55, 7.55, 7.4, and another one, and a couple of 7.5s. All right, so the mean of those is 7.55. And then we can also do the standard deviation. All right, so notice in your standard deviation, I should have zoomed in. In your standard deviation, you've got a couple of different ones that you can choose from. The STDEV.P is assuming it's population. The STDEV.S is assuming it's sample. This is a sample in this case, right? So we'll select that one. These other ones are the old ones. So the .P and the .S are the newer ones for the newest versions of Excel. So scroll down to sample, and then those 10. So we get 0.10274. Then if we want our test statistic, then remember we're comparing this against 7.5. So I would do the 7.55 minus 7.5, and then divide by the standard deviation divided by the square root of 10, not 109. That's how we would calculate our test statistic, right? Would you agree? Just, okay. All right. So we get 1.538-ish. So will we reject in this case? No. All right. So with T, it's harder to calculate the p-value because with T, we only have the T's associated with certain alpha values, right? They give you a T of 0.05, sub 0.05, sub 0.2025, and so on down the line. You can get bounds for your T. That was scary. You can get bounds for your T, or your P value, I mean, but it won't give you you can't read a good approximation of the P value from the T table because we don't have enough T values that are spread out for different values, right? However, in Excel, you have, let me get out of that. Sorry, let me zoom in so I can actually see a little better. In Excel, I don't know if I made that any bigger. You've got the T distribution built in, so you can actually put in the T distribution and get the probability associated with a particular T value. But it also doesn't, it does that, and it also does an inverse idea. But if I did T distribution, this says two-tail, and this says right-tail, okay? So we wanted the two-tail one, so let's say we did the two-tailed student T distribution, so let's do that. Our X value, of course, is up at the 1.53, at number 13, and we had 9 degrees of freedom. So in that case, our p-value would be 0.15, which is not very small.
This will all be on the YouTube.
Yeah, I'm recording. Yep, it's all on there. I'm recording. At least I should be. Hope so. If not, I'll re-record it and post something up there so you can see it. We're going to do more with Excel here in a little bit too, with some other type of tests that we're going to do where we're going to absolutely want Excel to help us do it. All right. So this two-tail idea would give you the p-value associated with it. You can also get the t value, the critical values for t. If I start typing this in again, notice it's got the t inverse in here. So instead of having to look it up in a table, you can get Excel to get the values that you want. So we wanted a two-tailed test for t, right? So the dot 2t is the two-tailed. So if I scroll down to that one, we wanted the probability to be 0.05. That was the two-tailed probability, right? And we had 9 degrees of freedom. Now, if I remember how this function works correctly, it should spit back out the 2.262. There we go. Good. I did remember how it works correctly.
So for the line 15, how does that one know like your alpha?
It doesn't. This is just giving you the p-value.
You don't need alpha for that?
No, remember for p-value it was what's the probability? Yeah,
okay.
yeah. And notice if I would have done the one-tailed probability for that one, as a matter of fact, since it's a positive t-value, it would want the right tail. That's what the t.dis.rt means. Okay. So if I did this one, it should give me half of that, hopefully. Yeah. So that's the right tail. So I know it doesn't record me writing on the board, but it is what it is. All right, so remember that our critical region was two-tailed, right? Our test statistic was over here, didn't hit out into that right tail, right? But when we're calculating p-values, we still treat it like it's a two-valued test. So when we did the right tail, this number, calculates this area. But since it's a two-tailed test, I've got to double it because it could have also been this side. Because we're doing it that it's just not equal to. So that's why this two-tailed number is double that number. So when you do p-values for two-tailed tests, basically you do the same probability as you did in one tail. You just have to double it because it has to go to the other side too. Your especially if you do not reject, your p-value should always be bigger than your significance level. That's what it means to do not reject, right? You're not in your significance level area, okay? If this number had turned out to be 0.04 or something, that would have been, that number looks like it's lower than your significance of 0.05, right? Right? If that probability would have turned out to be 0.04 something to be above that, it looks like it's less than your significance, but remember you're doing a two-tailed test. So you would still want to double that to 0.98, 0.098, and then it would be above your 0.05. The moral of the story is make sure that you double the value if you're doing your p-values on the tail. Again, like I said, especially if you're not rejecting. If you're not rejecting, the p-value has to be bigger than the significance value. Doesn't make any sense otherwise. You can always phrase your rejection statements in terms of p-values. Reject if your p-value is less than alpha. Do not reject if your p-value is greater than alpha. You can always rephrase them that way too. Does that make sense? Anyway, so this is the same. This is what you would do to do hypothesis testing for means. It's just like what we did for proportions, calculating the same sample statistic, and the sample statistic looks exactly like what we did for doing confidence intervals. Let's do one for differences of means. I'm skipping around because it's all the same thing. It's just depending on how you calculate the different things. It's all the same process, though. So if we look at, say, 7.3-6, we've got forces required to pull studs out of a window, manufactured for an automobile. The null hypothesis is that the difference of these two means, the difference of the two forces, is 0. So it requires the same amount of force to pull stud number 3 out as it does stud number 4 out. And then it says against a two-sided alternative. So the two-sided alternative would be that they are not 0. The difference is not 0. Alpha is 0.05. It says assume that the variances are equal, because when we assume the variances are equal, then we use that pooled estimate for the standard deviation, right? So we've got 10 observations for X, 10 observations for Y. Those are small samples. Variance is unknown but equal. Means we're using what distribution? What distribution do we use if the variances are unknown but equal? Well, if it's small sample, we'll use T, right? And as long as the variances are equal, we'll use the degrees of freedom and the pooled variance idea. If they're not equal, we use that Welch's T and had to do that nasty formula for the degrees of freedom, right? So in this case, how many degrees of freedom do we have?
Or the atom and then minus 2?
Yep, atom and minus 2, so it would be 18, right? So I can look it up in the table, or I can use Excel again here. Two-tailed test, and I want the T value that tells me rejection. So I'm going to use the T inverse command and two-tailed. So the probability we want is 0.05 because it told us a 0.05 significance level again, and we had 18 degrees of freedom. So 2.1. 2.101.
That's T of that.
Yeah, so that is, I'll write it down. That is T.025 of 18. Is 2.101. You can look at that in the table too. I was just playing with Excel because I hadn't done that yet. So just to show you.
And on Excel, you use the inverse.
Yeah, we use the T inverse, right? Yep. So I'm out of time. Using Excel real quick. So you want to read me the numbers so I don't have to look.
111.
Okay.
120.
Okay.
139.
Okay.
136. 138. 149. 143. 145. 111. 123.
Okay. And the other ones?
152.
Oops. Go ahead.
155. 133. 134. 119. 155. 142. 146. 157. 149.
Cool. Good. I need the means for both of these. Boom. There's both the means, right? And then I need the variances for both, because remember for But we have small samples, but we're assuming that they're equal. We have to pool the variances, right? I do a weighted average, so I need the variance for each. So var.s is your variance, sample variance. So get the variance for each. I'll pool it. Remember how we pool? We take the number of items in your sample minus 1 for the first group times the first variance. Number times the second. Number minus 1 times the second, and then divide by the total number minus 2. We did pooled variance for the last test, right?
You're supposed to include the mean and the variance. You included the mean when you did the variance.
Well, where was that information like 5 minutes ago? Thanks, Sid. I'm just teasing. Gotcha. Thank you. No, I was not supposed to include the mean and variance. All right. Thank you. All right. So we'll do 9 times the first variance, because that's 1 less than the number of sample, plus 9 times the second one, right? And then divide it by 18. That's our pooled variance. Remember doing that? Roughly? Okay. Then we have to do our sample statistic. I'll do that off to the side. We want the difference of our means. And then our purported mean is 0, right? That's our null hypothesis, isn't it? So then I just need to divide by the square root of the pooled variance times the reciprocal of the sample, the sum of the reciprocals of the sample sizes. Remember doing that? Remember that from the confidence interval? I know I'm a little way late. Sorry. Negative 2.04. Do we reject or not? Because it was two-tailed. This was our two-tailed value, right? So it's either above this or below the negative of this. It's below. Is it below the negative of that one? No. So we don't reject in that case. Okay. Sorry, I just wanted to show you that one real quick. All right. Have a good one. We'll do more of this next time. Sorry I kept you late.
It's not okay.
I know. I suck.
Worst Friday ever.
Worst Friday ever? Really? Wow.
I'm about to go get a winery burger.
Oh, that makes a much better Friday then.
Maxine's here.
Oh, really? Tell her I said hi.
I will.